Hello. So far with graphing polynomial functions, we have focused on the end behavior. What is happening on the far ends of the graph? We've totally ignored the stuff that there's crazy stuff going on in the middle, and that's what we're going to look at today. Can I figure out what's going on in the middle of this function? And to do that, I want to help you remember what we talked about with intercept form for quadratics. So if you recall, intercept form for quadratics had the appearance of y equals a times the quantity x minus p times the quantity x minus q. And the p and the q told us what the intercepts were. If you remember, if we have a quadratic that's factored, we can use the zero product property to find the zeros. What would make this turn to zero? So we are going to apply that idea to larger polynomials today. So you'll see how those x-intercepts apply in higher degree polynomials. Also, do you remember what those other words are for x-intercepts? Remember how we also call them roots, and we call them zeros, and we call them solutions. Those words are all still applicable. So let's go over to Desmos so we can see what this is going to look like here. So I have a function graphed here for us, and I want to look at the picture in connection with the equation that we see. So we have an x minus 4 times an x minus 9 times an x plus 3. So it's a little harder to tell when it's in factored form, but what would the degree of that be? So, well, how many x's would get multiplied together? Well, we have an x from the x minus 4, we have an x from the x minus 9, and we have an x from the x plus 3. So there's going to be x cubed as the highest exponent in this. We'll talk more about multiplying polynomials together, I think it's next week. So, but for now, this is degree 3. So think about Simon Says. What would that look like? Degree 3. Okay, so it's an odd. So what are you going to do with your arms? Yes, they're going to go different directions. So one up, one down, but we got to figure out which way. So that will come from looking out front. And I don't see anything out front of these parentheses here. So that means my A is just an understood 1. So it's positive, which means it's going to look like it goes uphill from left to right. So that means something like this with the end behavior. So now look at your graph. Now, ignore the crazy stuff in the middle, but if you read it from left to right, can you see that overall there's uphill? I know there's a little roller coaster action in the middle, but it does fit our end behavior discoveries. So now I want to talk about the roots, though. When I say roots, I'm saying the intercepts here. Let me zoom in a little bit more so we can count by ones. That'll make it easier. Oh. So let me click on these so we can see what our roots are. Okay, so look at those roots and look back at the equation. Do you see any connection between the numbers that you're seeing as the roots and what you're seeing in the factors? Well, let's see. Let's take this one factor at a time. I see an x minus 4 factor. Do you see anything in the graph that's connecting you to the x minus 4 factor? Yeah, that would be this 4 right here. Think about what value you can fill in for the x in the equation over here that would make that parentheses turn to a 0. Well, 4, if you put a 4 in place of the x, 4 minus 4 would turn that to a 0. Remember, these roots are also called zeros. So 4 is one of the roots. You can think of it as x minus, and that next part tells you what the root is. So x minus 4, so 4 is a root. Now look at the next factor, x minus 9, and then look at your graph. Do you see this root over here at the 9? Okay, so x minus 9, that root is a 9. If you plug the 9 in for the x into your factor right here, 9 minus 9 would make that parentheses turn to a 0. So for the zero product property, that would give us a 0. Now this next one's a little trickier. I see an x plus 3. I thought it was supposed to be x minus something. So what would that root be? Yeah, that would be a negative 3. And if you look at your picture, that makes sense. X minus a negative 3. You can think about breaking apart that positive sign, or think of it this way. If I focus on the x, what plus 3 would make that factor turn to 0? Well, I would need a negative 3 plus 3 to turn that factor into a 0. So you're seeing what the roots are when we have this polynomial given to us in factored form. We generally call it factored form instead of intercept form. I don't know why. I think they should be interchangeable for these because it does tell us the intercepts. Let's try another one. Let's try y equals negative x squared times x minus 6 times x plus, I don't know, 5. Okay, so this is kind of a weird graph. I'm going to zoom out a little bit so you can see it. Oh, look at that. Okay, so let's see if we can figure out the end behavior. So ignore the picture for a minute. Just look at your equation. So I have an x squared, so that's xx, and then there's an x in the x minus 6 factor, and there's an x in the x plus 5 factor. So this would be a degree 4 polynomial if I count that up. So degree 4, that's an even, so they're going to go the same direction. Now, when I look out front, I see a negative. That's why you see the arms. Now you can look back at your graph. The arms going down on this. That makes sense with what we studied with end behavior. But now we want to look at this stuff in the middle here. So the roots. The roots are the zeros. It's where it hits the x-axis. Now, sometimes it goes through the x-axis. Sometimes it bounces off of it. So we're going to talk about that in this problem. So, oops. Okay, so this 0, this x-intercept is at negative 5. Look back at your equation. Does that make sense to you? If I plug a negative 5 in for the x, negative 5 plus 5 makes 0. So it would turn this to a 0. So there's one of your roots. Let's look at this one next. This 6, okay, that makes sense from our middle factor here. If I put a 6 in for the x, 6 minus 6 would be 0. So that would turn it to a 0. So that's my other root. So, or x minus, you see the 6. So now that leaves this one. So at the origin, something weird is happening. In the last graph, our graph passed through all of the roots. This one, it passes through 2 of them, but it's bouncing off of this other one. Now that root is coming from our x squared here. So if you think about just that much of it, just if I just said y equals x squared, what parent function would come to mind? That would be a parabola, right? That's what's happening right there. If you can zoom in, oops, I don't want to stretch it like that. What if I want to look just at that part of the graph? Doesn't that look like a parabola? Now, when I zoom out, you see that there's more going on, but the part right around the origin there looks like a parabola, and that's because of the x squared. If you have a factor that is squared, that's going to be what we call multiplicity 2. It's going to make it bounce off of that root instead of passing through it. So that's why we see the bounce there. Well, let's see, I'll change one thing here. Let me go up to my x plus 5, and I'm going to put a 2 on that, and look what it did to my root there. See how it also bounces off of that one, just like it's bouncing off of the 0. So if you have an exponent on a factor, well, an even exponent, it's going to make it bounce off instead of just passing through. So now let's see if I can give you an equation, and we're going to try to kind of predict what the graph will look like before we actually do it. So let me scroll a bit here. So let's try this. Let's look at y equals a negative 0.2 times an x minus 2 times an x plus 5 quantity squared times an x minus 7. Okay, so now we're just going for a real rough graph. If we want a beautiful graph of this, we are using Desmos, okay? We are not killing ourselves making a table of values with this, nothing like that. We just kind of want to know what to expect from the graph, because when you look at Desmos, you might not see the whole picture based on how you're zoomed in. So you need to know whether you need to zoom in or out to get a better view of what's happening. So that's all we're going for here. So we're going to kind of make a sketch of this here. I don't know what that green mark is down there. Let me get rid of that. Okay, so first I would like to figure out the end behavior for this thing. So if I'm thinking about what I know about end behavior, I need to know what the degree of this thing would be overall. So I'm going to count how many x's I have. Well, I have an x in the x minus 2 factor. That x plus 5 factor is a double. Okay, see the exponent of 2 on the outside of that? So that counts as 2. And then I have an x minus 7 factor. So this is going to be a degree 4 polynomial. So degree 4, that's even. So what's going to happen with your arms? They're going to go the same direction. Okay, they're going to match. So I don't know if they're up or down until I look out front and see if I have a positive or negative. When I look out front, I see a negative sign on this one. So this is going to end going down. So I'm going to kind of sketch that on here first. Now this is not going to be beautiful. I'm just going to put some down arrows here. I know on the ends it's going to go down at some point. Okay, now let's see if we can figure out our roots. And I'm going to color code them. So this factor, the x minus 2, what x value would turn that factor to a 0? Well, that would be a 2. So I'm going to put a purple dot right here. What x value would make that x plus 5 factor turn to a 0? Well, that would be a negative 5. So 1, 2, 3, 4, 5. This one. And this is going to be a bounce. It's a double root. So you're going to see it bounce off of the graph there. Let's look at this last one, the x minus 7. So what x value would make that factor turn to a 0? What could you plug in for the x? Something minus 7 is giving you a 0. Well, that would be a 7. So 1, 2, 3, 4, 5, 6, 7. Right here is that root. Okay, so I'm going to put together what I know here. So I know that it's going to end on the left side going down. And I see that this is a double root, so it's going to bounce off of there. If I'm going to make it go through the purple, at some point I got to turn around and head up this way. And then at some point I got to turn around and head back this way. Now, I don't know how high and low this thing is going to go. We have Desmos for that. This is just to give you a rough sketch, okay? Nothing really fancy here. Do not stress about this skill. So let's go over to Desmos and see what this would look like. So I'm going to graph this. So y equals a negative 0.2 times x minus 2 times x plus 5 quantity squared times x minus 7. Close that parentheses. Okay, so looking at this graph. Oh no! Undo. There. Okay. I'm looking at this graph, and I look back at what I sketched. Okay, yeah, I had the idea of it. So it's not beautiful, my sketch, but I had the idea. So I just want to know like what to expect on these kind of. Now there's a little bit of vocabulary we should talk about with these. So we've talked about like maximums and minimums. So there is an absolute highest point on this graph. Do you see it? What's the absolute highest point? Yeah, it's right over here. This is the absolute maximum. We can also refer to this as the global maximum. Think global like the whole world. In the whole world of this graph, that right there is the highest you will ever go. Global maximum or absolute maximum. Now, there's another point that's like kind of a high point when you're looking at it, and that occurs over here. So this is not the absolute highest point, but can you tell that it's higher than like the graph right around it? You know, if you stay close, this is like if you go to Memorial Park in Newcastle, and you stand on the big hill, you feel like you're kind of like on top of the world. you are not at the highest point in the entire world. You are not at the absolute maximum. But if you're higher than the points around you, we say that's a local maximum. So yeah, that hill might be big for Henry County, but it's nothing compared to, like, I don't know, the Alps or something. So that point, -5, 0, that is a local maximum. Now, do you see anything that you would flag as a minimum here? See any low points? Well, yeah, if you look down here, that's a low point. Now, is it the absolute lowest this graph ever goes? Well, let's see. Nope, it definitely goes lower than that because it keeps going down forever. Okay, so this graph does not have an absolute maximum, or said the wrong word. It doesn't have an absolute minimum. It does, however, have a local minimum because that's a low point in the graph. If you look just right around it, like if I zoom in so I can look just right around it, then that appears to be a low point, but it's just a local minimum. So that's some vocabulary for you. Oh, also turning points. So anytime it switches direction on you, it goes from being a positive slope to a negative slope, or a negative slope to a positive slope. It's turning direction. We'll just call those turning points for now. So let me show you what you're going to do in your homework today. So it's going to be a page from your book. We're going to do 5 through 11. Now on 5 through 8, it specifically says use a graphing calculator to graph this. So I want you to use Desmos. Sketch it on Desmos. Do a little sketch on paper here, and then label on there if you have any turning points, global maximums, local maximums, global or local minimums. So just kind of put little arrows and label things. Okay, so that should be easy. Don't spend a lot of time making beautiful sketches. Just give me a picture of it. Then on 9 and 10 and 11, you're going to do what we did in our last example. So before you touch Desmos, I want you to think about what would the end behavior be on this. Get your arrows on the ends, which way it's going to go. And then find your zeros, your roots. Mark any of them that it's going to bounce off of. If it's got an exponent on that factor, it'll bounce off of it. And then draw a little sketch of it. It's okay if it's not beautiful, all right? I'm not going for perfect here. I'm just going for an idea of what it's going to look like. And then you're welcome to sketch it on Desmos and see how you did. So I think that is everything. So remember that Jesus loves you, and so do I. So do your math.